about something with a very long title.
Yeah, very long title indeed. I'll try to make this quick so we can all go for lunch in time. So my name is Jack Wolf from the University of Toronto, and I'm a PhD candidate. I'm working on the Performance Spectra-based design for the CSRN guideline for supplemental dampers. In this presentation, I will just focus on two aspects of this methodology, and it's the generation and the use of performance spectra for optimized damping design. So to put the presentation in context, when we're talking about efficient performance-based design of structures of dampers, we need three pieces of information. One is we need the controllable system variables that affects the system response. And secondly, we need the performance goals that we wish to achieve. And finally, we need the mean to achieve the performance goals. The idea behind the performance spectra-based design methodology is that we arrange all these pieces of information in a graphical format such that it's called performance spectra. So the performance spectra are tools that relate system performance of a equivalent SDOF system to controllable structural responses. So an engineer would come to a performance spectra and search for an optimal solution in SDOF domain, and then convert that SDOF system solution into a MDOF structure through a systematic procedure, such that the MDOF structure will achieve the initial performance goals. So central to this concept of performance spectra-based design is the performance spectra, and these are graphical tools that relate the system response to controllable structural parameters. And shown on your left would be a performance spectrum for hysteretic damper, and over here is performance spectrum for viscous and viscoelastic dampers. So to better explain the performance spectrum is an example of hysteretic damper performance spectra. Each of these performance spectra, or P spectra, because it's a mouthful, it's identified by a fundamental structural period of the base structure without any dampers, as well as the strength of the base spectra, expressed as a percentage of the elastic base shear. So normalized response axes are normalized base shear, acceleration, normalized drift, and normalized residual drift. These responses are normalized in such a way that if you have an undamped structure with that's linear elastic, the response will lie at 1 and 1. The inelastic undamped structure will be on your bottom right, and you can see that typically those structures will have a larger displacement response depending on the structural period, obviously, but much lower base shear response. Any retrofit options involving supplemental damper would be identified by, for example, the red dot on the screen. And in this particular example, you're looking at maybe 0.65 of the elastic base shear, and maybe 50% of your elastic displacement per minute, and maybe about 40% lower in residual drift than your inelastic undamped structure. Each of these solutions is identified uniquely by damper parameters. In the case of hysteretic dampers, we have a stiffness ratio, which is defined in such a way that decreasing alpha means increasing supplemental damping stiffness. There's also the damping ductility, which is decreasing damping ductility is increasing activation level. So for each solution that you select based on your performance target, you can identify them uniquely using two parameters, which then you can use them to transform into an MDOF structure. So to generate these spectra, there are typically two ways. The first way is the most straightforward one, using nonlinear time history analysis on equivalent SDOF systems. This is most accurate, yet it requires ground motions, which is not always available in the design situation. So more practical for design is a simplified method to generate a performance spectrum. And this only takes the co-uniform hazard spectra, UHS, and although it's approximate, it provides a simplified framework to explain the complex system behavior for systems with dampers. So go into the simplified method a little bit. Essentially, this is an equivalent linearization method which accounts for combined hysteretic and viscous and viscoelastic damping in the structure, and accounts for the effects of random response, which is relevant to earthquake excitation, obviously. And this basic postulate is that the normalized displacement are products of two independent modification factors. RDT represents the modification in displacement due to the change in period once you raise the structure with dampers. And RDC represents the effect of adding damping. So without going into too much detail, simply speaking, RDT is defined as the ratio of spectral displacements at the effective period of the damped structure versus the initial undamped period. The tilde on top of SD in this case signifies that this quantity actually accounts for the effective random vibration. Similarly, we can define a effective damping, C effective, accounting for large viscous damping and hysteretic damping, as well as the effective random vibration. Using this parameter and an extensive nonlinear time history parametric analysis, we derive the damping modification factor RDC. So using these formulations, we can predict the normalized displacement given the damping parameters that we select from the performance spectra. As for the base shear and acceleration, these are not generated from equivalent linearization, but instead are generated based on a displacement demand that we obtained previously. For systems with hysteretic dampers, everything is displacement dependent, so this relationship is quite straightforward. For systems involving viscous damping, however, we need an estimate of the system velocity. And for these cases, the normalized phase shear and acceleration are given by this expression here, which is the product of two factors, A and RAH, where RAH is sort of a harmonic response envelope, assuming that the system with viscous damping responds in some kind of harmonic manner with an effective frequency, and A accounts for the non-harmonic effect, which we call velocity effects. To better illustrate what I mean by these effects, we compare two time history records from two ground motions. On the left, we have a California motion, and on the right, we have a motion from Montreal, which is known to have high frequency content. In the California motion, because we have a relatively large frequency content at the structural period, typically, the quasi-resonant response will dominate, and the harmonic envelope shown in black here give a fair prediction of the maximum phase shear. On the other hand, if you have high-frequency excitation, typically the response will not be your elliptical response that you expect from resonance, but instead a jagged and irregular response due to local pauses in velocity and viscous force. And this effect is accounted for by the factor A. So using these tools, we can generate performance spectra using the simplified method without running time history analysis at all. And these are some samples of generated performance spectra from the simplified method. There is also a rigorous error analysis based for this method, but due to time constraint, there's no time to discuss that. And next, I'll touch briefly upon the issue of residual deformations for systems with dampers. Because residual deformations are typically dependent on the earthquake ground motions that occur after the peak response, and that information is unfortunately not available if you're designing the system using only the UHS. So therefore, naturally, they're less predictable than the peak responses from the simplified procedure. So therefore, the recommended design approach that we've taken for the performance spectra-based method is to do a crude estimate using the maximum residual, which I'll show you what that means. And this gives you the absolute upper bound of residual drift that's possible in your system. However, the problem with this approach is that usually the maximum residual is overly conservative and will not meet your performance target. And if this is the case, there's a more refined approach using what's called a free oscillation residual. To better illustrate the difference between these two estimates for bilinear and trilinear systems, you can refer to this figure. So imagine that you reach a peak response at some time during seismic excitation. If you stop the system and let it unload statically, you reach what's called the static maximum residual. This represents the absolute upper bound of residual drift. However, most systems have a tendency to oscillate away from that residual because there's some finite strain energy stored at that point. So the system will tend to oscillate inelastically, even without external oscillation, into a residual drift that's called a free oscillation residual. In other words, if you let the system oscillate freely at the maximum response and ignoring the ground motion effect, you end up with this residual drift. And as you can see, this one is much less than the static maximum residual. And we have conducted a very extensive nonlinear time history analysis using about 150 nonlinear oscillators with supplemental damping. And we can show that. So on the two figures above, we have hysteretic dampers and viscous and viscoelastic dampers. So the dots and the bars represent the mean and one standard deviation of the residual drift against the ductility. And the dotted envelopes are actually from the free oscillation residual. So you can see that there's a pretty good upper bound of residual drifts when you use the free oscillation residual, and it's a useful tool for design. So the next thing I want to talk about is the use of performance spectra, either generated from nonlinear time history analysis or simplified procedure, for optimized design of systems with dampers. And this points to a few notable results regarding the sensitivity of damping solutions that the engineer might potentially select, as well as the possibility of consider simultaneous retrofit options involving supplemental damping and traditional retrofits such as stiffening and strengthening. So the first result that you notice from the performance spectra is obviously the sensitivity to damping parameters. For instance, for hysteretic dampers, we have two notable regions over here and here, where in this particular region, the displacement response is highly sensitive to damping ductility. Whereas in this region, where you have low damping ductility, the force response is highly sensitive to the damping ductility. So naturally, when you're selecting solutions, you want to avoid those places. Even if your target performance is over here, you want to move your target displacement response further close to this corner, therefore to get a more stable response. For viscous viscoelastic dampers, on the other hand, with respect to the added damping, viscous damping factor C, you can see that for C less than about roughly 30%, you have large displacement reduction with respect to increasing C. Beyond that, you're getting reduced displacement reduction. Furthermore, large C is directly proportional to the damper force, which you need to carry to the foundation, and which you need to design all the rest of the structural members for. So increasing C beyond 30% might actually become detrimental, because some of the existing structural members might not be able to take the viscous force. Also, notes that slight increase in damper ductility, in the damper stiffness leads to a large decrease in this residual displacement. So that's something to consider. And this information is immediately obvious in performance spectra. And for example, an engineer might select ideal solutions in the proximity of those 2 points. Furthermore, performance spectra also reflect the effects of different ground motion frequency classes. Again, comparing the LA and Montreal ground motion suite, you see, so this is the spectral displacement curve of the two suites, the average spectral displacement curves. And you can see that for high period structures in Montreal, which is known to have high frequency excitation, you get low to negligible change by decreasing your period. You get low to negligible reduction of the displacement by change of period. So this is an indication that at high periods, in, for example, the Eastern Canada, supplemental dampers may be less effective. And this is manifested in the performance spectra for Montreal. Shown here are two performance spectra at periods of 1 second for hysteretic damper and viscous viscoelastic damper in 2 seconds. And you can see very clearly that performance spectra at 2 seconds, you have small displacement reduction coupled with large base shear increase. If you're using viscous dampers, you can further reduce the displacement. However, because of the velocity effect that we spoke about earlier, you're going to get a high increase in base shear. So these things should be of note when engineers are designing for retrofit using supplemental dampers. Also, by rearranging the performance spectra in the matrix form, when you have different periods and strength, you can consider options where you retrofit the structure by including supplemental damping as well as strengthening and stiffening, or vice versa, weakening or flexing of the structure. So, and also, when you want to consider, let's say you have a base hazard level and you selected the solution at this point. The spectra of T equals to 2 seconds and strength of 40%. And you wish to consider a higher hazard, which often is the case. All you have to do in the performance spectra matrix is to read off the response at a lower normalized strength. The reason for this is that the normalized strength is directly inversely proportional to the increase in hazard. For this case, you brought down the normalized strength from 40% to 30%, which represented an increase of hazard 4 over 3, which is about 30% increase in hazard. And the normalized response to the increased hazard will be given by the same alpha line and a constant displacement, constant yielding displacement of the hysteretic damper. In this case, it's RD over EF mu D. And these parameters are immediately available on the performance spectrum, and can show that a similar relation exists for viscous dampers and viscoelastic dampers. So it makes it really convenient to evaluate solution at different multiple hazard levels. Finally, we're currently in the process of expanding the P-spectra design method to advanced dampers such as the self-centering electric brace and the viscoelastic plastic damper. Many of you will know that the self-centering brace is mainly efficient in controlling the procedural drifts of the structure, while the viscoelastic plastic damper is optimal for designing with multiple hazards. In this situation, most of the frequent earthquake and windstorms will be dammed out by viscoelastic damping, while under large earthquake excitations, the damper will activate, capping off the damping force and dissipating the energy through hysteretic actions. So finally, performance spectra-based method is currently being implemented as a standalone supplemental document to the ASC 41 for the Canadian damper design guideline. So the structure of this, so the performance spectra-based method is going to integrate with ASC 41 in such a way that the assessments that you perform on your structure to be retrofitted using the ASC 41 to be used as direct inputs for the performance spectra-based design. From the P-spectra-based design method, you generate trial designs of dampers with supplemental damper, structures with damping, and then you can use the ASC 41 to reevaluate the performance of the structure. So in conclusion, we've gone over some of the generation techniques and use of performance spectra for optimal damper design. And currently we're working on integrating the ASC 41 with the P-spectra method, as well as including some of the newer results from advanced dampers, such as the self-centering and viscoelastic plastic dampers. And hopefully that guideline will be available at the end of this year. So that concludes my presentation. Do you have any questions?
Any questions for Jack?
How does your method account for vertical stiffness irregularities?
Vertical stiffness irregularities is, it's a good question, by the way. That's actually not touched upon in this presentation because that's a problem transforming SDOF systems into an MDOF structure. Right now, there are two ways to account for vertical irregularity. One is we have a modified damper distribution function, which is not presented here, which basically distribute supplemental dampers in such a way that you fix the vertical irregularity while adding the supplemental damping to reach the SDOF performance that you selected in the first place. The second alternative that we're looking at is actually to separate this into a two-stage retrofit problem. One is to use displacement-dependent devices such as hysteretic dampers to fix the irregularity initially, and then once you have a regular structure, you can apply another iteration of the P-spectra design method to get the damping result that we want. Anything else? No lunch?
Well, I don't know if lunch is here, but you can join the presentations next door. I think we should still have one left, but thank you very much, Jack. And if any of you have presentations to